All right, so I have a video that basically does an overview of limits with different methods, going through everything that you need to know sort of for the assignment. But I thought I would go into more detail about using tables, especially because that seems to be a struggle for students. You know, how do you get the limit from the table? How do you know how to set up the table? Um, how do you read the table to find the limit? All of that kind of stuff. So a limit is something that you're essentially introduced to in calculus, but you've seen it actually in algebra when you learn about end behavior of polynomials and then asymptotes of rational functions. When you're looking at end behavior and asymptotes, you're really finding a limit, but we're not introducing it in those terms. We're kind of talking about the concept, but you don't really know the formal definition. But a limit is basically when you ask yourself, as I approach this x value, what happens to y? You're basically looking for the behavior of your function, the y values, as x goes to certain things. When we're looking at asymptotes, we will look at this and consider it for vertical asymptotes. As your x value is approaching where the vertical asymptote is, what happens to y? And for asymptotes, it usually goes to infinity or negative infinity. With end behavior, we're usually looking at what happens to x as we go to infinity or negative infinity, go to the edges, what happens to y, and then those also usually go to infinity or negative infinity. And you can even sort of think about it with horizontal asymptotes. If your x is going towards negative or positive infinity, you're going on the edges. What happens to y? And that's where you find the horizontal asymptote. Y usually approaches a number. So, but we're overall looking, okay, as I'm heading towards some x value, what is my y doing? And so our notation for limits, we have three different types of notation. The first is we use lim as the abbreviation for limit, and then underneath it is x arrow and then where you're heading. So there's usually a number in that place, or maybe it'll be the infinity symbol or negative infinity symbol. Then you have your function, the name of the function, f of x, or if it doesn't have a name, you'll actually put what the equation is, and then equals, and then what the actual limit is. Your answer is to the right. Generally, when we're looking at a limit, we're looking at what happens from both sides as you approach it from the left, and then when you approach it from the right, where is it going? If we want to only consider one direction, if we're heading only from the left or only from the right, we'll use plus or minus signs as a exponents, basically, after the number. And the plus and minus basically is telling you, are you coming from a negative infinity or positive infinity? Are you coming from the left or the right? So if you're looking at it just from the left side, we use the negative as sort of an exponent or a superscript. And if we want just to consider it from the right, we use a plus sign. Now, for what we're doing this week, especially with the assignment, we're looking at both sides. So we're not going to be dealing with this plus or minus, but when you get into calculus, there will be times where you have the plus or minus when you're finding limits. So there are different ways to find a limit. You can use a table, you can use a graph, or you can do it algebraically. And so I'm going to just focus on how you use a table to find the limits. And so we call this finding the limit numerically, because you're basically plugging in numbers, and then you're looking at a list of numbers, and you're trying to see, well, where are those numbers heading towards? Does it look like they're approaching a certain value? Tables are not good for every situation. A table is a good method if you have something that's undefined. This is great if you have vertical asymptotes or if you have like holes in your graph. So they're really good for rational functions to use a table, because let's say you want to know what happens as your function approaches 2, but when you plug x equals 2 into your function, you get undefined. Well, there's no answer there, but we can use the limit to kind of guess where it would have gone. And so you can use a table to kind of approximate where it would have gone, even though at that particular value it's undefined. Tables are also good if it's non-continuous. So this just means there's a break in the graph. So maybe this is, you have a piecewise function that doesn't connect. Also, rational functions are also can be are non-continuous because you have asymptotes. But that would be like, okay, if I'm looking at a certain value and there's a gap. So if I'm going to just draw a graph here. But let's say I have something that's non-continuous, where I have a graph and a point, and then maybe there's a jump, and then it continues or something like that. That's a good spot to use a table to kind of see, because at that jump, you don't get a good idea. You know, it's possible there may be a complete gap. You may not even have a point there. And you could even have something like this. Excuse me. Drink some water. So you may have a point where you have an open circle and you don't have a function value. It's non-continuous. There's a gap, but it's still, there would be a number there. Like if you look at the graph, you're like, okay, if I were to fill in that hole, where would it be? So tables are good in those particular cases. So if you have like maybe a piecewise function or a rational function, that's a good way to use a table. But you do not want to use a table if you're asked for a limit at infinity, because the whole point of the table is to plug in numbers close to your value of interest. But infinity there is not a single value. There's no way to really plug in a numbers and get close to infinity because it goes on forever. So, for example, the last question on the assignment is a rational function, but it's asking about infinity. So you don't want to use a table there because you can't really reach infinity with a table. It's just you want to use a different method to do so. So, and you can do that by graphing or by using our algebraic methods. I would not use a table in that last one. So a lot of people ask me, well, how do you determine how to create your table? So I've done my best to kind of explain the process here. So it's good to have at least 7 values so that you can get enough data. And I prefer having an odd number of columns just so that the middle is the one that you're asking about. And then you have things on either side. So it's like kind of a mirror image. So like the middle box here, if I'm looking for the limit as x goes to 2, I would put 2 in that spot. And then I'd be looking to the left of 2 and to the right on 2 on either side. And you kind of have a mirror image. And so like step 2 here, if it's x approaching 2, then where I have a here, I'll just put the number 2. And so you would have your x values here, and then like your function values or your y values underneath. Then your whole goal when you create a table is you want to get really, really close to that value you're interested in. But you know, it's like, how do you determine how close you get? So the best way to do it is with powers of 10. And you're basically adding powers of 10 to the left and to the right. You're subtracting when you're on the left, you're adding to the right. And it's like you're just moving a decimal place away. And that way you're getting really close to your value. Because that's the whole point of the limit, is to get close to it. And you don't want to just pick random numbers. You want to see as you get really close, as you get closer by another decimal place, what happens. So if you know you're approaching 2, you can plug 2 in for a, and you can use this table to basically come up with your numbers. So I've got many examples where I'm going to go through this so you can see the whole process of creating the table and then how you read that table to find your limit. So here we want to use a table to estimate the limit as x goes to 2 of x minus 2 over x squared minus 4. So this is a rational function. This is a good thing to find a limit for with a table. And so we're looking as x approaches 2, so our place of our interest point is 2. That would be basically our A. So I would have 2 in the middle, and then I'm basically adding and subtracting powers of 2 on the left and the right. So it's a little bit easier if we look on the right first. 10 to the negative 3 is just 0.001. So we get 2.001. 10 to the negative 2 is 0.01. So you can see that we're just getting like a decimal point away as we move to the right. I'm basically just plugging in 2 for A and then putting my calculator and just understanding what the powers of 10 are doing. And then you want to do the same thing on the left side, but now we're subtracting these powers of 10 from 2. So I get 1.999. This will give me 1.99, and this will give me 1.9. So on the outer edges, we're near 2, but as we go towards the middle on our table, we're getting closer and closer to 2 by just adding more decimal places. This is how this table works. Is your middle point is where you're interested in, and then you want to get closer and closer to it from the left and the right. And this is how we approximate this limit. Now you don't have to set up your table like this. Question 1 on the assignment gives you the table, but I would recommend using this sort of setup for like question 2. Question 2 does say to use the same sort of method as question 1, which means to find the limit using a table. So I would set up your table for question 2 similar to this. So that way you can, you'll really get a good picture. So I filled in, these are my X values here. And when you're making the table, you don't have to show the first row that I have that. I have that there just to demonstrate how the table is set up, but you don't need to do that. You can just go straight to the X row and then the Y row. And then what you do is you plug these numbers into your calculator, into your actual function here. So you're basically looking at y equals x minus 2 over x squared minus 4. And you plug each of these numbers from your table into that equation, and then you write the answer. So if I start at the middle, plugging in 2, that is, if I plug 2 into the denominator, I get 2 squared, which is 4. 4 minus 4 is 0. Dividing by 0 is undefined. So this is why we want to use a table, is because at the value of 2, we don't actually have a number. It's undefined. So we have to use this table to approximate, well, what would it have been if we have, been on the left and the right. Now, I'm going to show you how to use Desmos to your advantage, because plugging these into your calculator can get pretty tedious. So I am actually going to use the graphing calculator portion of Desmos to do this. It will also give you a good visual. But what I would do here is, so first off, let's just define our function. We'll use function notation. So we'll use f of x. And I'm looking at here x minus 2 over x squared minus 4. Okay. So you can get a visual here of the function. Let me make sure yep, okay. So I'm going to create a table, and actually if we put a equals and then our value of 2, that a is what we're looking for, I can hit the plus sign here and go to table, and then you can see I've got an x and a y kind of thing here. So you can, and I think this is going to work, if I say equals f of x and then underscore 1, this should, I might just need to do that. Okay. So I can replace my y1 with f of x1, so it can use this function here, and then we'll use whatever I plugged in for x here. So I'll fill in my table. And what I'm going to do is I'm going to just take that table that I had filled in with the A minus whatever stuff, and you can see it gives your value. And then this way, if you have this, all you need to do is reuse this table, change your function, change whatever A is, and then you can get the numbers instantly. So this is going to save you a lot of time. It should be an x minus 1. So I am just literally typing in my table the setup that I gave you. If I can type properly. Get up there. Okay. A. And then we've got A plus 10. Oh man, I'm really struggling with the typing today. -3. A plus 10 to the -2. A plus 10 to the -1. So I'm going to just make this so I can kind of overlap these. Here we go. So I took this table and I've put it in Desmos in such a way that I can now reuse this. If I'm taking limits of different things, all I would need to do is change my function here and then change whatever is the value that I'm approaching here. So this will save you a lot of work once you type this in, and then it gives you all of those function values that we need to write in our table. And the table is good in this method. If I just briefly turn off the table, if you were asked to find like the limit as x goes to 2, you don't even realize that it's undefined at this point because the graph doesn't look like it's undefined. So the graph is a little misleading, and that's why the table is kind of nice, because you can see, okay, it actually doesn't exist at that point. There's a hole, but we've got to kind of decide, well, what would be the number that would fill in the hole? And you can't even really get that from the graph because, I mean, you've got decimal points here. You'd have to kind of guess, and it'd be really difficult to do it graphically here. But the table is really nice because I can look at the table and I can look at the pattern and say, okay, well, what is the most likely number that would fit in where undefined is? Because that's essentially what our limit is. And so your numbers are getting close to 0.25, and then they're getting closer and closer to 0.25 in this direction as well. So the most logical number that would be in this spot if it wasn't undefined would be 0.25. Based off of the pattern that we're seeing here. So I'm going to copy in our table onto our screen here so that we can see that. And rounding, I mean, I'm going to just use 3 decimal places. But this is really nice because you can just copy it off of Desmos and just make sure you round your numbers properly. Oops, and that one, when it rounds, it's 0.2499, but that actually rounds to 0.250. So I fill in my table. Now as x equals 2, basically, we have a value that's undefined. But now that I've kind of rounded on the table, you can see on either side, it's 0.25. And so our limit is the best guess for what would fit here. You know, if it wasn't undefined, what would be the logical number based off of the pattern? And based off of the pattern, because we've got 0.25 on either side, when you round it, it'd be 0.25. So when it says use a table to estimate this limit, you have to first create your table, find the function values, and then you have to kind of determine, okay, where am I? The middle is what you're interested in. So I don't know if it helps to like highlight that this is where you're interested in, because that's where our x is approaching as x approaches 2. And then you have to kind of guess, well, what would be there if it wasn't undefined based off the pattern? So you're really just following the pattern. And then once you determine what that number is, you need to write your answer. So I see a lot of people actually forget to write their answer after they fill in the table. So the correct way to write your answer would be the limit as x goes to 2 of x minus 2 over x squared minus 4 equals, and then what that number is that should be in that gap if you follow the pattern. It should be 0.25. So you have to actually say, what is the limit? You have to give me some answer there. You can't just fill in the table. You have to actually answer the question and give a limit using the limit notation. Are there any questions? Okay. Here's another one. We've got another rational expression here, basically, that we're finding the limit of. We've got x squared plus 3x plus 2 over x plus 1. And this time our limit is x equals -1 that we're looking at, as x, or not x equals, as x approaches -1. So this number is our a that we're interested in. So I'm going to put -1 in for a, and then I need to add my values to -1. And those are just powers of 10. Whoops. Just putting like a little mark there just to remind you what you're adding. And with negatives, you have to be careful because, you know, it's not like -1.001 to the right, because we're adding it to a negative. So to the right, it's actually -0.999. And then we have 0.99, oops, negative, and then -0.9. And then the left side is now where the numbers appear to get kind of bigger. You have -1.001, -1.01, -1.1. So we're just adding and subtracting powers of 10 on either side to form our table. And then we want to plug those numbers into our function so that we can figure out our limit. So since I've got Desmos set up so nicely here, so I'm going to just change my function to match what our new one is. We have x squared plus 3x plus 2, and then x plus 1. And now we're interested as x approaches -1. And so these are our function values. This is the output for our table here. 0.9, 0.99, 0.999. Again, we're undefined, which is why we can't just plug in the number. Number -1. -1 will make your denominator 0. Then we have 1.001, 1.01, and 1.1. So I'm going to just move this over so I can actually see it while I write on my table. Plug in our numbers. We have 0.9, 0.99, 0.999. We have undefined at -1. then 1.001, 1.01, and 1.1. So when we're finding the limit here, we're basically asking what would be the number that would fit in well at that location if it wasn't undefined. Basically, what could be there if it wasn't undefined? And if you're looking at the pattern, it looks like, well, 1 would be the logical number there, because on the left, we're getting really close to 1. On the right, we're now above 1. So it looks like a value of 1 would fit in with that pattern there. And so that is our limit. So the limit as x approaches -1 for your x of x squared plus 3x plus 2 over x plus 1 would be 1, because that appears to be what that missing number would be if it wasn't undefined. The number 1 would fit in really well in that pattern. Any questions? Okay. Here's another one. I'll use a table to estimate the limit as x goes to 0 of x cubed minus 2x plus 6. So in this case, it's not a rational function, it's actually a polynomial, but we can still use a table to estimate what the limit would be. So in this case, our value for a is 0. We're approaching 0. And so then this is 0.001, 0.01, 0.1. And then the nice thing about it being at 0 is it's just a mirror image. And so now we want to plug these numbers into our table. So go back up to Desmos. Now my function is not a rational, it is a polynomial. So I can just plug in my polynomial there, and now we're interested in 0. And then I've got my table here. So I'm going to fill in my table with these values: 6.199, 6.019, and 6.002, 6. And I'm going to round these all to 3 decimal places. So I'm going to just fill in my table. 119. I have to be very careful about rounding. This rounds to 6.020, 6.002, 6. We actually have a value at 0, so we don't have an undefined or anything. We actually have a value there. So I filled in my table with the information that I got from Desmos here, and our point of interest for our limit is when x goes to 0. Now, in this case, we actually have a number. So the number that x is when x is 0, this is the limit, because we actually have a number there. We don't have a gap or anything like that. So if you actually have a value at that point, that's your limit. And you can see the numbers on the left are getting closer to 6. And on the numbers on the right, as you move towards the middle, they're getting closer to 6. So the point at x equals 0 x equals 0, we plug it in, we get 6, and that is our limit. So our limit as x goes to 0 of x cubed minus 2x plus 6 is equal to 6. It's basically the number you get when you plug in x equals 0. It's a little silly to find a limit in a case like this because you can just literally plug in the number, but it does show that the table can give you the answer just like it does if there's something undefined. You just literally read off the table, and if there's a number there, well, that's going to be your limit. Are there any questions on this example? Okay. Now I'm going to start throwing in some trig stuff because we do the first example on the assignment. It involves trig, so we can still use our Desmos to do shortcuts here. So we're using a table to estimate the limit as x goes to 0 of 1 minus cosine x over x. And so a is 0 because we're approaching 0. And the important thing to know about if you're doing limits or you're given functions here, always assume radians. So in math, when we work with functions, cosine and sine, tangent, we rarely actually have our calculators in degree mode. It's always assumed to be radians unless you are told otherwise. So you just want to get used to the fact that you need to have your calculator in radians, and you're going to do everything in radians. We generally never convert to degrees unless it's a real world situation where it makes more sense to figure out your angle in degrees. But generally, it's always in radians. So you need to make sure if you're using your calculator that you are in the correct mode, you're in radian mode, because if you are in degree mode, your answers for your table are going to be completely wrong. So always make sure your calculator's in radians unless you are told otherwise. Our table here is going to be exactly the same as the table in the previous example because we're still approaching 0. So I'm going to pull up Desmos here. Now Desmos assumes radians just like math, basically math when everything is assumed radians. Desmos is operating in radians. So when you enter in your thing, you can be sure in Desmos that it's going to be in radians. So Desmos knows cosine, sine, all of that kind of thing. So I can put in my function 1 minus cosine x over x. We're still interested what happens as x goes to 0. And then I've got these numbers here. So, and these are all, it's all based off of radians. And if you can convert it, I believe, yeah. So if you hit the graph settings here, you can see that it's set to radians. If you convert it to degrees, all of your numbers are going to be really, really small. That's an indication that you probably messed up. You want to make sure it's in radians and it defaults to radians. So you can always double check in Desmos that you have it on radian mode. And so this is the table, and I'm going to be rounding these to 3 decimal places to fill in with my table up here. And then we're going to look at that table to determine what is this value that would be at this part where it's undefined. So I've got negative point. I've got, I think, 3 decimal places. Make sure that I'm rounding this correctly. That is I hate when it gives it to me in scientific notation because then I have to mentally write down what does that mean and then round it properly from there. It's the downside is that it is giving you the in Desmos here. Let me pull it back over. This is giving it to you in scientific notation. So if I need to round this to 3 decimal places, I need to actually convert this to what the number looks like and then round it. So it's a little harder to do. I have to kind of do that in my head or write it down. So when I round that, that comes to negative 0.001. Then we've got undefined. And then in this case, it actually is almost a mirror image. But now we've got positive numbers on the right. And so that's what our table looks like. And so now, because again, we have this undefined value, we're trying to figure out what could go here. And you want to basically pick the most obvious number. You know, you don't have to round it to some complicated decimal or anything like that. You just pick the most obvious number, which would be 0, because you've got negatives on the left, you've got positives on the right. 0 is kind of the natural place to put right there. So our limit is going to be 0 because that would fit in with our pattern here on our table. So the limit as x goes to 0 of 1 minus cosine x over x is 0. That is the natural spot that would fill in the undefined if it wasn't undefined. Any questions? Okay. Here I'm throwing in something with an exponent. So we've got 2 to the x minus 1 over x. And again, we're doing x approaches 0. It's very common. It is extremely common to look for limits as x approaches 0. It just shows up a lot in math. So there's a lot of special limits that you'll learn about in calculus, which are when x goes to 0 and they give you special numbers, and it's just, you know, they're special. Like you just learned that anything in this form always has a limit of this value, and that's the way it is. So I'm going to go back to Desmos, and now we're going to change our function. I'm putting my parentheses just for the top here. So 2 to the x minus 1, and then divided by x. And we're still interested as x goes to 0. And so now this is my table that I'm plugging in here. And so we have to kind of guess, okay, what goes into this location here. Looks like it's going to be close to 0.69 something, you know, but it's not going to be just 0.69 because that's above 0.69 and it keeps getting bigger. So let's round these and then just kind of figure out, okay, what would be logically in there. So I'm going to pull this over so I can write it on the screen and round just to 3 decimal places, and just be very careful about the rounding. I wish that I could show the Desmos on the same time as I'm writing on the screen, but it won't let me while I'm in presentation mode. So you'll just have to trust that I'm rounding these correctly. And hopefully I am. I'm not making any mistakes. Nope, that rounds to 700. 8. Okay. So I've rounded my values and we're trying to figure out, okay, what could be in this spot that's undefined. Rounding on the left, we got 0.693. Rounding on the right, we have 0.693. So it seems like, okay, this is probably 0.693 for the limit. Now, if I didn't round to 3 decimal places, let's say that I rounded to like 4 or 5, or let's say you were using all of the digits that you see here, what you can do alternatively is to find the average of the values on either side. So you can add this and this together, divide it by 2 to get an approximate middle point for that part here. The whole reason that I'm rounding to 3 decimal places is so that you don't really have to do that. You kind of end up with similar numbers on either side, and then you can just say, okay, so that must be the middle number to follow the pattern. But if you use more decimal places, you can average the 2 values on either side to kind of get an approximate for the middle here that's missing. So our approximate value for the limit is 0.693. So limit as x goes to 0 of 2 to the x minus 1 over x, 0.693. And you can look up, this is actually, there's a formula for this limit to kind of determine what the limit is equal to, because some of the limits equal special numbers. And I think this one is actually the natural log of 2. Yep. So this actually comes out, the limit is the natural log of 2. When natural log of 2 has a lot more decimals, we had to kind of round, but it actually has a special formula that you can learn about, like in calculus, to how to determine that the exact value of the limit is natural log of 2. When we find limits with tables, we can't generally find the exact value of the limit. We're finding an approximation. So we're not going to get the exact number for natural log of 2, but we get something that's close. And this is important when you're looking at problem number 2 on the assignment, where you're filling in the table and then asks you what famous number it's approaching. You're not going to get the exact famous number. You're going to have to then kind of figure out, well, what number is this close to? And you may have to look it up if you're not familiar with the number. Like, people are not going to have memorized that the natural log of 2 is 0.693 something something something. So you might have to look it up, but it gives you an approximation. You're not going to get the exact limit when you're using a method like this. Are there any questions? Okay. Here's another one I'm throwing in with trig. So we just want to find the limit of sine of x when x goes to -3. So -3 is our spot of interest here. And then we're looking on the left and the right side of -3. And hopefully you've seen enough of these that you kind of understand the pattern of creating the table. That's sort of the point here is, oops. It'd help if I don't write the same number twice. But there's basically a pattern to how you create the table. So that you get to a point where you don't even need to kind of notice or learn my trick here. You just kind of say, okay, I just have to be close to this value on the left and the right, and just kind of following this pattern. So bringing Desmos over. Again, we want to make sure that we are in radian mode. And now I'm interested in -3. And so this is another one where we're actually given a value here at -3. So our limit is actually going to be whatever that number is here. So I'm going to round these and put them on the table. Just being very careful about my rounding. And so since we actually have a value here, this is our limit. And we can even say our limit is sine of -3 because, you know, that's, if we didn't want to give the rounded value, you can give the exact value. It's the sine of -3 because that's what we plugged into x. And you can see that that value is the average, the value on either side. So if you did the average method to kind of estimate the limit in the middle there, you would get the same approximate rounded answer of -0.141. So our limit as x goes to -3 of sine of x, you can say is sine of -3, or approximately -0.141. Now we had an example earlier where we actually had the exact value of the limit. That was when we were looking at the polynomial. And I didn't bother writing, like plugging in. It's just a whole number there. So I just put, okay, it's equal to 6 because we got a whole number. But in this case, it's an approximate value. We have a rounded value, but it is simply just sine of -3. So you want to give the most exact value as possible, which is why I wrote sine of -3 so that you don't have to do with any rounding there. But if you round it, that's fine too. That's just an approximate limit. Any questions? Okay. Here we've got a natural log in our limit. We've got the natural log of x over x minus 1, and we're finding the limit as x approaches 1. So I'm going to just fill in my table. And then I'm going to pull up my Desmos. Now, unfortunately, like I can share a link to this, but I don't know if you are able to save it in your own account. You might be able to if you have a Desmos account. Otherwise, you might want to just set this up yourself and then save it. I'm actually going to save this. That way, when I share the recording, I'll share the link, and then hopefully you can then just modify this yourself. And if you just, Desmos accounts are free. So if you make your own Desmos account, you can save it, and then it's in your list of saved graphs. So that might be something you want to do so that you can reuse this. But I'm going to enter in, so natural log, and Desmos knows what that is. So that's really nice. Okay, and see, you have to be very careful because I didn't put parentheses around the natural log of x, and it wanted to put the x in a fraction, but the whole natural log of x is in a fraction. So that's why I had parentheses there. So we've got the natural log of x over x minus 1, and now we're interested in 1 here. And so this, again, it's another one where it's going to be undefined, so we have to kind of guess where that value is. And just looking at the table, I would put 1, because we've got things above 1 here, below 1 here. 1 seems like the natural filler for this missing piece, basically, where it's undefined. So we've got 1.054, 1.005, 0.001, undefined. This one actually rounds to 1 when you round it to 3 places. And we've got 0.995, 0.953. So if you were just looking at our rounded values, you might say, okay, I'm going to average my two values, 1.001 and 1. And this would be 1.0005. That could be a potential limit if you're just going to do the average of the left and the right side. But the advantage to looking at it with Desmos and seeing all of the numbers is that you can see, okay, it's probably not 1.0005. It only looks like that because we rounded. But if you look at the full values, or at least more decimal places, you can see that 1 is the more natural limit. And usually the problems we give you are going to be, whole numbers or things like, like fractions, things that come out real nicely. So you can assume that if you had a choice between guessing that the limit is 1.0005 or 1, it's probably going to be 1. So kind of using your table where you've rounded in tandem with the table in Desmos can help you give a better idea of what the actual limit is, which in this case, 1 makes much more sense. So the limit as x goes to 1, the natural log of x over x minus 1 is equal to 1. And then this is my last one, and this one I picked because it has this exponent up there that's very similar to what you would see on our assignment. So we're interested again as x goes to 0 of this nasty looking thing. So you want to be very careful that you type it into Desmos correctly. Just going to fill in my table. So I got to have all my parentheses in the right spot here. 1 plus 5 parentheses. Now Desmos does know what E is, so you can just use the letter E. X minus 1. And then up in the exponent again, -1 divided by x. Okay. And then we're interested as x approaches 0. Again, we have undefined here. Now these numbers, most of everything that we've done so far, the numbers have been very similar or very close together. So it's kind of easy to fill in what the average is or what the limit is. Here, we've got big gaps. We've gone from 68 to 134, and then we've got either side here, 146 or 149. Like they're not as close as some of our other ones that we've looked at here. So this would be a good one where you'd want to take the average to kind of approximate what that middle point is going to be, because it's not as obvious looking at the numbers here because they just have huge gaps between each one. Sometimes you might want to get even closer by doing to the -4th to see if you can get it even closer. You might want, instead of my table here, you might want to add 2 more and use get even closer if you want. But the best way for us in this case is just to take the average of these 2 values to come up with an approximate estimate for the limit. So I'm going to round these values. This is 68.412, 134.680, 146.941, undefined, 149.909, 164.532, 638.465. So we can't really, it doesn't really look obvious what number might be in between 146.941 and 149.909. So let's average these values to approximate the limit. And we'll just use our rounded values here. So when I average those, I get 148.425. So we'll say that is our approximate limit is 148.425. So our limit is x goes to 0 of 1 plus 5 times e to the negative x minus 1 to the negative 1 over x, 148.425, because that's the best thing that we can come up with based off of our table here. Is we're just going to average those two values to come up with an approximate middle, and then that is going to be our limit. Now, if you look up this formula, this is another one where it's a special formula. The actual limit, which you would not be able to find from the table, but the actual limit is 5, or no, not 5, e to the 5th power, which is 148.413. So our table got close, but there's no way from the table to know that the actual limit is e to the 5th. Like, the table can't tell you that. The table just gives you an approximate value, and that's why there's other methods. Graphing wouldn't be able to tell you that either. So the best method we use is finding it algebraically, but that's what you learn about in calculus, where you learn all the rules to find the exact limit. But for now, we're just estimating the limit using a table, and so that gets us something that's relatively close, but not exactly there. So are there any questions? Okay. So this was basically everything that I had. Hopefully this has helped you kind of understand what we're doing here for the first couple of problems on the assignment, and kind of helped you determine, especially with problem 2. Problem 2, you're going to have to do something similar to this, where you're going to have to kind of find the average, and then you're going to actually have to kind of Google the formula to figure out what that value is if you don't actually know it.